Hello everyone, welcome back to the channel. Today we're continuing our LeetCode challenge as part of my interview prep. So we're going to be tackling problem number 110, which is balanced binary tree. First I'll break down the problem visually so it's easy to understand, then I'll walk you through the code step by step, and finally we'll take a detailed look at an example going through each iteration of the code in action. Alright, so we're going to dive in. And we're going to start out reading the instructions. So given a binary tree, determine if it's height balanced. So what does height balance mean? So me reading the definition, it says a height balanced binary tree is a binary tree in which the depth of the two subtrees of every node never differs by more than one. What does this mean? So if we start with 3, we look at the subtrees. So what are these subtrees? Right here the height is 1, and right here the height is 2. So 2 minus 1 equals 1. Therefore we know that starting from the root point it is height balanced. Now let's look at a counter example. If we look at it from this point, the height will be 1, and if we look at the subtree on this side, we can see that 1, 2, 3, so the height will be 3, and so 3 minus 1, that is 2, therefore it is unbalanced, and what it wants us to return will be false. If, like the bottom example number 2, it is unbalanced, then we will return false, and if it is true, then if it is balanced, then we will return true. So in order to do this, we can determine from each node, right? And if we visit each node, we would have to then find the height of this one, this one, this one, and this one, and then going down we would find the height of this and this, and that is repetitive work. So what we can do is actually start ourselves at the bottom, and in order to do this we can do it through depth first search, and through depth first search we will reach the bottom and then calculate the height, which will be from right here, and we can determine that the height, say for this example, is 1 on this side and is 1 on this side. So what we can do is write this function, use this function, the max of the left, and then the max, and then from the right. So using this, we can then add it. So 1 plus the max of the left and right will give us the biggest height, right? So whether it's the left or the right, and add 1 to it for the previous iteration. So let's go through this example and see how this works. Alright, so starting right here at the bottom, we can see that this is a height of 1, and are they balanced? The base case will tell us that if it is null on the left and if it is null on the right, 0 minus 0 equals 0. Therefore the difference is not greater than 1. So yes, this is balanced. Let's cross that off. We know by the same logic that the left side is also balanced. And what is the height of this? It is 1, so we know that the height is 1, and we will be returning that information to the previous node. So now from this side, from starting at 20, we will determine if it is balanced from the left and the right, and we know that the height was 1 and 1, so 1 minus 1 is equal to 0. It is not greater than 1. Therefore we know that this is all balanced, and now we know that we need to return the height of this. So using the function I showed and the little code snippet, we can return the height at this level. So returning that will be 2, and then compared, now we will go back up here, and we will have to look at the left and the right. So looking at the left, we can see that 9 is it's only 9 there, so the left side will be 1 and the right side will be 2. So 2 minus 1 is -1, but we only care about the absolute value. So 1, is that greater than 1? No, it is actually equal to. So we have to be sure that we look for this. If it is less than or equal to 1, then we will return that it is balanced, right? It is balanced. So the height and the whether it is balanced will be our two factors, right? So it will be like this. We will return it in a tuple. I'll explain more in the code. The tuple will either be true or false, and it will return the height on this side, right? That will be our answer, and in the end we will only need this section. So now going on to example 2. I'm not going to work this out, but if we can see and this example, this is the example we're going to be working on further. And now, what is the space complexity and the time complexity? They will be O of n. And so this is because we will be going through each node on the tree exactly once through recursive travel. Therefore the time complexity be O of n. And for the space complexity, we know that the depth of the recursion stack is proportional to the height of the tree. Therefore, in the worst case, the height of the tree can be as large as O of n, right? So we'll only visit this node, then we'll visit this node, and then we'll visit this node, and not again. Perfect. So now we're coding the solution, and the first thing that we will need is to define our depth first, or to make this the first search. So we will pass in a root, and the next thing we will need to do is define the base case, which will be if not root, then return a tuple which will be true, and the height will be 0. So after that, if this is not the case and the node does exist, we will need to find the left and the right. And so DFS, we will go through this iterative or recursively. So left dot or root dot left, and then we will find DFS of the root dot right. So we will go into the left and the right subtrees. And what do we need to do? We need to know if this is balanced. So how do we find this? We just find if it's balanced by the left and the right, and this will be at index 0. Why at index 0? Because index 0 will tell us if it is balanced or not with the true and false. And how do we get a false? We can get a false if through this way. And let me just write this. So the absolute value of the difference of the left height from the right height, and the height is at tuple index 1, right? So if it is less than or equal to 1, and that should if this evaluates to false, then we know through the properties of AND that it will then balance will be false, because true true, and false will evaluate to false. After that, we need to return this function, and it will return a tuple, and it will be balanced. And also on the other side, we will return the height, so the max of right, or the max of left, 0, and right, 0. Actually, it is 1 because we are looking at the height. Perfect. So return, what will we return? DFS. We will pass in root, and all that we need is to pass in index 0, which is true. So let's try running this. And perfect, it accepted it. And let's look at this, submit it, and perfect, we see that it was accepted. And now let's look at the walkthrough. Alright, so now we are going through the detailed walkthrough, and so we are starting at on node number 1, right? So we are starting at the root, and the root will be 1, so let's write this right there. So if not root, we know that we will skip this section because it does exist. So if we look at the left, what is the left? It will be 2. So we write 2, and what is the right? The right is 3. So do we know if it's true or false? And do we know the height? Not yet. So let's follow that. So we are currently right here at node 2, and let's write that down, node 2. So what will be, we will skip this part once again, and the left of that will be null, and the right of that will be null. So how does that look? Let's look at it further. So if the root is null, as we can see, we will be in null, then we will finally go into this if not root. If not root, what are we returning? We are returning that true, it is balanced, right? It is balanced. And we are also returning that the height is 0. And so let's write that down. So we know that it's true and the height is 0. And we can also infer that the right will also be the case, since the right also is null. And so after that, let's move on to the next line. So what does this next line say? If left, right, we know that that is true, and if the right, that is true, and the absolute value of the two heights. So what is the height? We know that the height is 0 and 0, and 0 minus 0 is 0. So 0 is less than or equal to 1. That evaluates to true. Therefore, balance will be true, and we will return true for that. Now we will return 0 minus 0. We will return the max of 0, 0. So 1 plus 0, we know that is 1. So we will return this true, and that the height is 1. So returning that, we know that this is true and that the height is 1. So now let's take a look at the right. We can see that there is a lot more on the right side. So if we go and look at 3, we follow this. Now the root will be 3. Further down into this recursive, again we skip if not root, and looking at the left, what will be the left? 4. And what is to the right of 3? It will be 5. So the right will be 5. Now what is to the left of that? It will be 4. So let's follow to 4. 4. Now that we are there, what is to the left? It is null. And what is to the right? Null. So therefore we can infer, like from the previous version, that it is, we will get t0 and t0 for the left and right, because we have no children right here in the left and the right. Okay, so after doing that, we know that this will be true, this will be true, and the heights will be less than 1, so that is true, so balance is returned true. And the height of this is 0, so we will return 1 right here, and let's return that over here. So now we know that on the left we will return 1, right, because of 4. And now let's take a look at the right. So what is to the right? 5. So now we're going into 5, and in 5 we can see that we have null on the left, right? So on the left it's gonna be null, and on the right we have 6. So let's write 6 on top so we can visualize that. And we know that a null gives us true, it is balanced, and 0 is the height. So for the right, we will look at that. So now that 6 is our root, we can see that we skip if not root again. And let's take a look at this. So null, it will be null and null on the left and the right. So we know that this will return t0, which is true, and the height is 0. And so let's continue on further. So this is true, and 0 minus 0, it will evaluate to true. So let's return that. So 0, 0, this will return t1 again. So now we know that this will be t1, so true and 1. And let's see, so now that the left is balanced, the right is balanced, and let's look at the heights. So the left height will be 0 and the right height will be 1. So 1 minus 0 is still 1, and 1 is less than or equal to 0. So that checks out. That will still evaluate to true this time. So balance will be true. And then let's see. The left height was 0 and the right height was 1. 1 is bigger, so 1 plus 1 equals 2. So we will return 2 this time. So let's go over here. It will be t for true and 2. So the left will be balanced, the right will be balanced. And now let's take a look at if there's any difference. So the left will be 1, a height of 1, and the right will return a height of 2. So is 2 minus 1 is 1. Yes, that still checks out, and we can see that to be true for as of yet, because the difference of this side is 1 and the difference of this side is 2. So we're not quite there yet. So this will evaluate to true again, and we will be returning true for balanced, and for the left and the right we will have 1 and 2. 2 is bigger, so 1 plus 2 is 3. Now we will return true and 3. So after that, let's take a look. T1 and T3. So the left will be true, the right will be true, so they are both balanced, and the left will be 1 minus 3. Perfect. So what is 3 minus 1? It is 2. So is 2 less than or equal to 1? No, that is false. Therefore, that will evaluate to false, making this false. And so we know that if we had a node right here, then we can pass that on, right? So 1 would be right here, 3 would be right here, and so it would be 1 plus 3 equals 4, and we would pass that back. But since we don't, we will end right there. And remember that this is at index 0, so this is our final answer, and it will evaluate to false. So thank you for watching this tutorial. I hope it helped, and see you for the next time.